You know that feeling after a long day of studying, right? You flop down and think, man, I did so much work today. Well, what if I told you that according to physics, you might not have done any work at all? Today, we're going to dive into what work and energy actually mean in science. And trust me, it's way different and honestly, a lot cooler than just hard effort. All right, so let me ask you something right off the bat. Are you working right now? Just sitting there watching this thinking, does that count? By the end of this, you're going to know the scientific answer, and I'm pretty sure it's going to surprise you. Okay, so check this out. On the left, we've got all the stuff we call hard work, studying, thinking, even pushing against a solid wall until you're exhausted. But in the physics world, nope, none of that counts. Then you look at the other side, simply lifting a book, that's work. A coconut just falling from a tree? Yep, that involves work too. So what is going on here? This seems totally backwards, right? Okay, to figure out this whole paradox, we've got to get on the same page as the physicists. See, for them, work has a super precise definition. It has nothing to do with how much you sweat or how tired you feel. It's all about one thing, movement. And here's the absolute key to understanding it all. For scientific work to be done, there are two non-negotiable conditions. First, you've got to apply a force to something. And second, that something has to actually move. It has to be displaced. If one of those is missing, guess what? Zero work is done. It's really that black and white. And of course, it all boils down to this super simple equation. Work equals force times displacement. And that's exactly why pushing on a wall does no work. The force is there, for sure, but the displacement, it's zero. And anything times zero is zero. We measure all this in a unit called the joule. But wait, there's a little more to it. It's not just about if something moves, but also which way the force is pointing. Think about pulling a little toy car. You pull it forward, it moves forward. Your force and its movement are on the same team. That's what we call positive work. But what about a force that works against the movement, like friction slowing down a hockey puck? That force is actually doing negative work. It's taking energy away from the motion. Okay, so now that we've got a handle on work, let's talk about its partner in crime, energy. They're totally connected. You can think of it like this. If work is the doing, then energy is the potential to do. They're really two sides of the very same coin. This quote really just nails it. Energy is basically the capability to make something happen, to apply a force that causes something to move. And since they're so closely linked, guess what unit we use for energy? You got it, the joule, same as work. And man, energy is everywhere and in so many different forms. You've got heat, the chemical energy in the food you eat, the electrical energy powering this very screen, light from the sun, the list goes on. But for today, we're going to zoom in on just one type, mechanical energy. All right, so let's dive into this idea of mechanical energy. It really breaks down into two main flavors. One is all about motion, and the other is all about position, kind of like stored up readiness. Let's tackle them one by one. First up, we've got kinetic energy. The key word here is motion. Anything that is moving has kinetic energy. A car on the highway, that falling coconut we mentioned, you running for a bus, all kinetic energy. And the formula is pretty cool. 1/2 times mass times velocity squared. That little squared is a huge deal. It means that doubling your speed doesn't just double your energy, it quadruples it. So let's put some real numbers to that. Let's say you have a 15-kilogram object, not super heavy, and it's moving at 4 meters per second, which is like a brisk jog. That object is carrying 120 joules of energy. That means it has the capacity to do 120 joules of work, all just because it's moving. Okay, so what's the other side of the mechanical energy coin? That would be potential energy. And the key word here is stored. This is energy that's just waiting to be unleashed. Think about pulling back the string on a bow and arrow. The energy is stored in that stretched string. Or winding up an old toy car. The potential is locked in that spring, ready to go. Now, the type we deal with every single day is gravitational potential energy. Seriously, anytime you lift something, a bag of groceries, a book, anything, you're fighting against gravity. And the work you do gets stored in that object as potential energy. The formula is super intuitive. It's just the object's mass times gravity times the height you lift it. So the higher you go, the more potential energy you store. Simple as that. Okay, now we're getting to the big one. This is arguably the single most important, most fundamental rule in all of physics when it comes to energy. It's like the ultimate law of the universe for this stuff. And here it is, the law of conservation of energy. It's so elegant and so profound. It states that energy cannot be created and it cannot be destroyed. It can only change from one form to another. That means every bit of energy in the universe right now has always been here and will always be here. It just transforms. The falling object is the perfect way to see this in action. Let's picture it. At the very top, just before it drops, it's holding still, right? So its kinetic energy, the energy of motion, is zero, but it's high up, so its potential energy is at its absolute max. Then, as it starts to fall, its potential energy starts dropping, but it's gaining speed, so its kinetic energy is rising. That potential energy is literally turning into kinetic energy. And right before it hits the ground, it has basically zero potential energy left, and its kinetic energy is at its peak. So here's the most important takeaway. If you were to pause it at any point during that fall and add up the potential energy and the kinetic energy, the total amount would be exactly the same. The balance shifts from potential to kinetic, but the total sum, it's constant. That right there is conservation in action. All right, we're almost there. There's just one last piece of the puzzle to put in place. Power. We've talked about work, which is getting a job done. Well, power is all about how fast you get that job done. Power is simply the rate of doing work. The formula couldn't be simpler. It's just work divided by time, and we measure it in watts. So think about a really powerful car engine. It's not just that it can do a lot of work. It's that it can do a ton of work in a really, really short amount of time. It's all about speed. This table is the perfect illustration. Take a look. We have girl A and girl B. They have the same weight, and they're climbing the same rope to the same height. That means they do the exact same amount of work, 3,200 joules. But here's the kicker. Girl A zips up that rope in just 20 seconds, while girl B takes 50 seconds. Because girl A did the same work in less time, she is way more powerful, 160 watts compared to just 64 for girl B. Same work, but totally different power. And that brings us all the way back to our starting point. That wall. If you push on it with all your might and do zero scientific work, why on earth do you get so tired? Where does all that energy you're obviously burning actually go? Well, it doesn't just vanish. Remember the law of conservation. The chemical energy from your food is being converted inside your muscles, mostly into heat. So while no work is being done on the wall, your body is still transforming energy. Something to think about next time you feel like you're working hard.